Hello, everyone. I'm very excited to be here today, all the way from Switzerland to beautiful Australia. And my first goal I already achieved. I arrived here, and I am coming from winter, so I'm very happy that I'm not red as a tomato right now. Thankfully, the weather is not that crazy. So this is Knuckles, my new friend that I made with my Pac-Man circle. I really love this analogy, by the way. It's really awesome. As was already mentioned, I'm a game designer working as a full-stack developer at Archeologic. We are a startup from Zurich that is working with 3D interiors and architectural visualization on the web. And we are basically working on a JavaScript web framework where you can use our 3D models and 3D API around 3D modeling for your website. I really, really love games. I like developing games, I like playing board games, video games, and that's why I'm here today to talk to you about render engines. And the second goal is that you come out of this talk and you know a little bit more about 3D, and that you know how to get started if you want to. So this is more of a low level talk where you will be able to learn, hopefully. Yeah, I really like traveling, but I have to say this has been a really long travel to come here. I might have to change this. No, it was really enjoyable so far, so thank you so much again for having me. So why would you want to do 3D on the web? I mean, the web as it is now, it's really great. We can do lots and lots of things. Why do we need 3D? So first of all, 3D adds completely another dimension to the web. That means you can also use this dimension for your advantage, to show more things. So this is a visualization that we made. And on top of this visualization, we don't only have a 3D model of a house, but we also have spatial data, which we can then use with our machine learning algorithms to, for example, automatically furnish your room and show you how you could use this space that you have not even thought about before. Or we can also see which is the room you might want to use for different things, or how the light is going to affect your room. It's not only that, we can also make really amazing games on the web. And we can use all the advantages of the native web that we have, which we could not do with applications that are just standalones. So this is a really cool prototype that Ada Rose was doing in a very quick iteration. So it was really fun to play. You should try it. You can also really do data visualization. So this is a data visualization from Visicities. And what I really love about this is that you can not only use the third dimension to show data in time, but you can actually also use it to show a progression over time. So you can use animation and other infographics to show these things. So I don't know how many of you have experience with working with 3D, but I myself was wondering, how do we even start with 3D? And like we have so many numbers, we have wireframes, we have polygons, we have textures, so many new things that we want to use. And how do we even get started? It's very overwhelming for beginners, I think, because I have been working with game prototypes, with 3D visualizations, with 3D on the web, with WebGL, 3JS, and it's still a mystery to me, and it's still really hard to help people to get started. So my approach is a little bit different. Yesterday we have heard lots of talks about color, and I really enjoyed, that was actually at CSS conference, sorry. Lots of color concepts, and I want to go one step behind that. So I want to talk about light and how we actually see. So let's take a blank scene and we add this scene to it. We have like a little chair, and we have a laptop standing on a desk, we have some shelves, but we have a window, and outside of the window we see the sun. And the sun is shooting rays or emitting rays onto the earth. And what happens is these rays come in through the window and they start bouncing off the first object that's in the scene. And this light ray has energy, and the light is basically going to bounce until this energy is used up. But what does that actually mean? So light is electromagnetic waves with different frequencies which make up the color. So if you take away one frequency or two frequencies, you might get red or green. But what do we actually see? So what happens with the rays, only the rays that are hitting our eyes are actually visualized on the back of our eyes. So how does it happen that different objects have different colors? I'm going to explain that a little bit later as well. Material surfaces have this thing where they selectively absorb different frequencies of light or energy, and they can also reflect the light or transmit it. So for a visualization, you could think about these three different types, and that's a really big abstraction. So you have materials like mirrors or water, mirrors or metals that are reflecting the light, which means that they are uniformly reflecting the rays, and through the uniformness, you will actually be able to see your reflection. Then you have things like diffuse materials, which are super chaotic, and they basically scatter the rays all around the place. And you have propagated light. So if you have a material like glass or water, the light will not only reflect off the surface, but it will actually also transmit through the solid. With these three different things, could somebody bring me some water, please? Thank you. With these three things, you can already create such a big range of materials, and we have not even talked about the colors yet. Thank you so much. And I know this might seem a bit random, but I'm explaining this to you because this is the problem I see with people that are starting. It's not just, if you get started with 3D, it's not just you have to learn how to 3D model. It's also you are basically a movie director, you are a light specialist, a photographer, you have to use lots of design to get to a point where you get some nice results. You have to know about scenography and lots of other things. So it's like a new big box to take things out of. And I feel that when I explain to people these concepts, they start to really understand what is materiality. How do we create a realistic looking 3D scene if we don't know about these things? So we have now the concept of light, but how do we capture this light on an image? And for that, it's really cool to go back to the first cameras that have been made. And these are called pinhole cameras, which most of you have probably heard of. And what happens is that we have one box with a tiny hole, which basically only allows us one light ray to pass per pixel, or in that case, space on the film. And that's where the concept of ray tracing is coming from. So ray tracing is a really substantial rendering technique that has been around for a long time. So the first talks about ray tracing engines were actually at SIGGRAPH, I think 1984. So that's 6 years older than I am. I feel pretty, it's pretty cool to see how long this technique actually has been around, because if you think about computer graphics, you think, okay, it's just been a few years since we have this GPU acceleration, and no, actually, I think the first computer graphics animations have been rendered with ray tracing, and other techniques that I will show you a bit later actually then took over and for real-time computer graphics as for games. But Pixar is still using, it's a mixed, kind of a mixed thing, but they're still using ray tracing as their primary way of rendering. So what is ray tracing actually? If you think about the sun and it's emitting billions and billions of rays at every tiny little microsecond, that's lots and lots of rays that are bouncing around all, yeah, okay, not really in this venue because it's quite dark, but that are bouncing around all over the place. And if we would calculate all these rays, that would be a big loss, because what I've said before is only the rays that actually hit our eyes are the ones that we can see. So somebody was really smart and came up with the concept of backwards ray tracing. So what we do is we go backwards from the eye, or from the camera in this case, and we go through the pixel, and we shoot the ray from our eyes into the scene, and we see which rays are going to hit a light source at the end of it. So these are considered the primary rays. We want to see what is the main object that gets hit, the first one, because that's the one that we want to visualize. And that's the beauty of ray tracing, is that we actually have this understanding of the scene, so we know what is the first thing we're hitting. And what we do is very simplified. We do a test, is this point, or this point of on top of the surface of the object, is it directly in sunlight? Or is it obscured by another object? So what happens is we hit the object, and from the object we cast a second ray based on the reflection. We cast a second ray directly to the sun. That's the simplified version, right? Sorry. But it gets a bit more complicated, since we have talked about materials before, right? So what happens actually on the surface of the object? What if our surface is transmissive? So what we want to do is not directly check if the point is in the sun, otherwise we just get two values. We get it's in the sun or not. So what we actually want to do is we want to see how much of our light gets reflected and how much of our light gets refracted or gets transmitted through the solid. And that's just a mathematical equation that we can do. And from there, we're going to see if it hits another object. And then we go on and on and on. And at the end, we want to see if we hit a light source or not. It's still very simplified. So I would like to look at some code that does this concept. I'll give you a minute to read it. Yeah, I think everybody got it, right? So what is a common challenge among people who do computer graphics is to write the most compact ray tracing engine that could actually fit on a business card. So that's what people do in their free time. And I was giving this talk at JSConf Iceland, and right after me there was Martin Kleppe doing a talk. It was called Daedalus. It was a fantastic talk, can only recommend it. But what happened is I think he did show me an example that was a fourth of this. So please watch it. It's really cool. I was I was very impressed. Very impressed. So there was almost no typing involved. Well, this is not really readable. I mean, this is how I feel after 2 weeks of looking at my code. Just don't understand anything. So let's take this a little bit further down. And I took all the math out of this because I think it's not really something we should look at right now. It would add lots and lots of slides. So first, we want to think about the concept of geometries. There is lots of primitive shapes that we can describe mathematically, and one of the easiest shapes are spheres, because basically what it needs to define a sphere is a center and a radius, and boom, we have a sphere, right? Cool. So we're only going to do spheres for the beginning. What we also want to define is the material, so we want to know what color does it have, how transparent is it, and how reflective is it. So what we want to define for these objects, or for all our primitive objects that we're going to program in the future, is an intersection function. So basically we get the ray, the origin of the ray and the direction of the ray. And we do check, does it hit or does it not hit? And if it hits, we want to know on which two intersection points, because there's always two. Then we're going to have our main function where we define our scene. This is going to be something you're going to have to do a lot, is you place objects in our scene. And because we have a simplified version of a ray tracer, we only do spheres. Also, our light source is going to be a sphere for now. And then we have a frame buffer where we have, for each pixel, we're going to check and see, we're going to trace our rays for each pixel, and then afterwards, when we have all the image data, we're going to render that to a canvas. So this is how a trace function could look like. And the cool thing is recursive, because we all love recursion. We take all our scene in, all the geometries. We take the first ray, the origin ray, which is the incident ray that we have seen before, and the direction, and then we also have depth, because basically what I said in the beginning, we want to trace the ray forever until it hits the sun. But that could really take a long time, or sometimes maybe it doesn't even do it. So that's really a shame, because we want to do this real time in the future. So what we do is, after the depth of recursion that we define, maybe 5 times, we do the check if actually the object is in shadow or in the sun. And we're going to do this for each light source in the scene. And then we can combine the values of the light sources together. And that's where the physical correctness of the ray tracer is going to end. So if you really want to have physical correctness, you would go for a path tracer. That's a whole other box, where you really shoot the rays forever and see when they're going to hit something. Where was I? Yeah. So we're going to find the nearest object, our first object that's going to be hit. And for that, we're going to loop through all the geometries. We do the intersection test for all the geometries. And if we hit something, good. If not, we're just going to return the background color of our scene. If we do hit something, we're going to have to see what object material is there. So if we have transparency or reflection, we have to continue the test, because the ray is going to bounce off. So yeah, we're going to do a recursion for each. So we're going to do a reflection recursion, and we're going to compute the refraction recursion. And in the end, we're going to put them together with Fresnel. And that's something I'm not going to explain. It's really cool, though, because it depends on where our surface normal is. So if we hit, sorry, that was too early. If we hit the object, it depends on what is the impact and where is the surface normal pointing at. And depending on that, we're going to change how we calculate the two values of refraction and reflection. Exactly. So if we resolve the recursion in the end and we compute the values together, we're going to get the color of the pixel at that specific point. And this is what it's going to look like. So it's really interesting. We already have lots of things. We have reflection, we have shadows, and these things come all for free with ray tracing. You're going to see that's not so easy with other rendering techniques. So I have already gotten ahead of myself a little bit. What strikes me, or what was really cool in this experiment, is that everybody can get started really fast to actually write a render engine. Okay, so very little code, we can do our own render engine. Great. But we're going to very fast run into lots of problems. For example, what if we want more than just primitive geometries that are not mathematically defined? What if we have multiple light sources that we have to consider in our calculation? What if we have more transmissive materials, or materials that are multi-layered, such as skin? So it's somewhat transmissive, but also it's milky and get really interesting. What if we want more physical correctness? Sorry, I have to get used to this. Yeah, what if we want to have more light bounces? And what if we want to avoid noise in our scene? Because that's something that we will always get with ray tracing, since it basically, one sample per pixel is not going to be enough. We're going to have to do lots and lots and lots of samples and add them together to get a really smooth image. Yay. Okay, so this leads me to the second rendering technique that's very fundamental in computer graphics, which is rasterization. And the interesting thing about rasterization is that it's really super fast, and it can do lots of things. But basically, what is the concept is that it's solving the visibility problem from a different perspective. While ray tracing is tracing from the eye to the objects in the scene, rasterization is going the other way around. So it takes the scene and it's gonna go from the scene to the eye with perspective projection. So what we do is we just basically flat map the whole scene onto a screen space version of that. And we are using triangles for this, because triangles are an ideal rendering primitive. It's planar. That means we don't have, we can always look at it in a 2D, from a 2D point of view, and we cannot make them any smaller. We cannot add more surfaces to it. So what we do is we map each triangle to screen space, and then we're going to rasterize over it and see which pixel lays in what triangle. And with the C buffer, we're going to see which of the triangles are more in the front and which one are more in the back, and that's how we're going to render it. So these are two really basic implementations. One is a basic rasterization implementation, and the second image is a basic ray tracing implementation. And you can see that as I said before, with ray tracing, there's already lots of things that you get for free. For example, reflections, anti-aliasing, shadows, soft shadows, and all these really cool things. I think everybody can see what is the quality difference. So how are computer graphics solving this? Because if you look at games these days, you're not gonna see the top thing. It's gonna look really nice. So with advanced implementation, you can actually fake a lot of the physics, but we're getting to a problem when it comes to transparency and water simulation of fluids and things like this. So there is differences. Ray tracing is physically correct, provides us with high details. It's super computational heavy, and we don't know yet, or we will probably never know if we can do it real time. There is some attempts, and they are super cool, so you should definitely check it out. And ray tracing gets really complex quite fast, so you're probably not going to work on a ray tracing engine on your own. Rasterization is really fast, so we can do it easily real time. There's lots of tooling and hardware support, so that means the GPU is actually made to support your rasterization shaders and algorithms. It's physically incorrect because, as you see, we lose, through the perspective projection, we lose all the information about depth and actual objects. We just make them flat. And therefore, we lose quality of the image. How do we do rasterization? How could we get easily started? We saw before how to get easily started with ray tracing, but now we want to actually work with rasterization and get our scenes together. So this is where I want to give you this toolbox. It's called A-Frame. And it's really awesome because it's a HTML component-based web framework from Mozilla. Basically, you can define your scene with HTML tags and attributes. So for example, you can add your sky with an image reference, or you can add rendering primitives such as boxes, spheres, cylinders, etc. By just defining positions, width, and other things. So colors, materials. And you can add lights. And the cool thing about A-Frame is it comes with WebVR support. So you have all the major headsets that are supported from the get-go, which also means that you have controller support. So it could look, for example, like this. It's really boring, though. So what do we do with it? I mean, it's still the primitives. It's not very exciting. That's where the community comes in. So lots of people from the community have been writing components, custom components that work super well. And here you can see how we would load such a component. So it's just basically loading a script source. The first one is A-Frame that we want to use. Then the second one is 3D.io, is the framework we are working on. And then we have some community examples like orbit controls, which controls like an object that could go around something else. And we have an environment component, which is really cool. I'll show you later what it looks like. So this is how our scene would, for example, be defined. We can use the custom A-Frame components to load objects, or to define, for example, in the environment at the bottom, we could define the preset that we want to be using. And really quickly, with a few lines of code, you get something like this. You get a really nice scene, very dreamy. You could just lay down and put your VR headset on and enjoy it. And I have to say, even if you are not familiar with 3D modeling, you don't have to. It's really a big overhead to get started with modeling, as I know that from my learning it. It's really a hard and steep learning curve. So this is way more fun to get started, and then you can see if that's something you would like to integrate in your product, or if you want to just get started and try to work with it. Which leads me to the problem of where do I get my content from? What do? I can't do 3D modeling. I don't know where to get proper resources from. And also, I don't know what is actually good 3D content. I don't know what makes a good 3D asset, what makes a bad one. And there we have a few things that you can do. So for example, this is A-Frames Inspector, which is also something that I can really highly recommend. Comes with A-Frames, so you actually have a 3D inspector where you can place your objects. And one of my coworkers was writing this plugin where you can load 3D models from Google Poly or from our library, and hopefully later on much more curated content. And you can just drag and drop them in your scene and then copy the attributes into your HTML. Because it's HTML based, you can also just use JavaScript to animate any of the attributes you want. And as you see here, you can even just define an animation, third, fourth line. You can just add an animation to any entity in your scene without any JavaScript. Sorry, JavaScript folks, you don't need it. But you can make it much cooler because you can then make interactive things. So I would like to wrap this up. The takeaway for everybody that gets started is your models matter, your materials matter a lot, because if you don't define your materials properly, you're gonna lose lots and lots of quality of your product. So your scene might look really bland, it might look gray, it does not get interesting when you interact with light. So please remember this. And also your lighting matters. So if you define your lights wrong in your scene, it's gonna look really flat. And sadly, I don't have the time to make a little introduction of that, but if you're curious, just come to me later and we can have a look at it. Also, ray tracing is really cool. I really love doing ray tracing, but it is still not ready, I think, to be used in real-time rendering. However, you can use ray tracing engines to pre-compute realistic light. So if you remember the scene from the beginning, there was actually a light map baked into the model, which means we have textures that contain the light information from a ray tracing engine that has been doing this computation for like an hour or so. And that's something that we also offer in our product. That's something I'm working on, is that we take a generic 3D model and we take the generic light setup that you choose and we basically bake it in your scene statically. These are techniques from game development that are really going to be helpful for the web VR scene and for everybody who works with web VR. So for that, thank you very much for your attention. And echidnas are awesome. They're my new favorite animals. Thank you so much for having me. And this is how to get started.